Hello. Hi. Good morning, everyone, and welcome to this talk. It's great to see so many people here at Connect and talk about VR over the last couple of days, last 3 days. It's been great. This talk is entitled Integrating and Profiling VR in your game engine, in your code base, using the Oculus PC SDK. So a bit of introduction. My name's Tom Heath. I'm going to give this talk with my colleague Scott Bassett. Both of us work in the developer relations group. So our role is to help developers such as yourself all around the world just to get the best VR they can, how to integrate our code into your code bases, and how to get great best practices and great VR experiences. So my background is I worked in the SDK group. I've been at Oculus 2 years. I've done a fair amount of work in exploring best practices and what works well in VR. Of course, as you all know, it's sort of an ongoing exploration into what works well, but we've made quite a few inroads. So this talk is, initially I'm going to be talking about integrating VR into your engine. So I'm going to present a couple of ways of how to do that in an easy manner, how to get your non-VR code bases and get them full of Oculus VR. Then I'm going to talk about some troubleshooting because it's getting VR right is very important, and getting it nearly right is kind of less comfortable. So we really want to sort of share our experiences of what we found with developers and help you troubleshoot that integration to make sure it's the best VR it can be. And then Scott will talk about a very important aspect of integrating VR, and that's profiling your VR to get the performance needed. Very crucial to having that presence in VR is having that solid frame rate. So Scott will be talking about that, about GPU view, and a little bit about Q ahead as well. So first of all then, integrating VR into your engine. So first step is to get the Oculus PC SDK. That's on our website. I'm sure the vast majority of you probably have had that, but it has runtimes as well that need to be installed. And lately also we need you to have the latest drivers because we're working with hardware vendors such as NVIDIA and AMD, and that's really helping to get the very best possible VR experience in terms of really good latency and other things. So when you have everything set up, when you have your everything plugged in right, just a tip for you that in order to ensure that when you've upgraded to the latest, that everything works as it should, then I very much recommend that you open the configuration utility, which you can find in the system tray in the bottom right corner of Windows, and open that up, and inside that there's a demo scene. And just firing that up and just checking that that's correct VR and that you're positionally tracked and you move your head and everything's working correctly. That's a very good check to see that everything is working right when you perhaps upgrade from one version of the SDK to the next. So a very important part of the SDK and integrating it well are the samples that we provide. So there's a whole suite of samples. The basic one, which has been around a while, is Oculus Room Tiny, and we've upgraded that over the time. So it's now extremely minimal, very clear to see in just a few hundred lines just how to integrate VR and get the right ingredients in there. In addition to that, we've expanded on that theme of minimal code and created a whole suite of Oculus Room Tiny samples, and they each show different facets of our SDK and including the different components of VR into your code base. So very concise examples. And then finally, Oculus World Demo. Again, that's been around a while. It's a code base that's larger. It has more aspects of the SDK being showcased within it, and although the source code is there for you to look at, it's not quite as illuminating as the small bite-sized Oculus Room Tiny samples. But nevertheless, the source code is there for you to look at. So I'm just going to outline two integration methods that are very popular and we can advocate. The first one is to use that basic Oculus Room Tiny demo and go through it line by line and just check that every one of the ingredients in that minimal sample is represented in your code base as well. And this is something that a huge number of developers have done, and it's a very successful way of integrating VR. So there is a GL version as well. So I guess the basic Oculus Room Tiny demo, that is very much the purpose of it. In addition to that, there may be developers who would rather than do it all in one go, would perhaps prefer a more incremental approach to adding in VR. So to take it a step at a time, so convert their non-VR applications to full VR. So for this, we've made a custom sample, one of the Oculus Room Tiny samples, and that's called Engine Integration. And that shows you, again, in very minimal source code, how to, each step that we recommend just to incrementally put in that VR into your code. So I'll go through the facets of this just briefly because it may be familiar to many of you. But actually, the SDK has moved on in time. It is still useful to go through it quickly, even for those that have already integrated the VR into their code bases, because there are little nuances that might be helpful in getting that integration right. So step one, very quickly, very basically, just getting the header files and the library files, including them, initializing the SDK, and initializing a single HMD, and just interrogating it, checking that it really is what you think it is, and that everything's working right, and then just closing down again. So a straightforward first step. And as I say, each of these steps is shown in minimal source code within this engine integration sample. So the second step we advocate is just getting those two render buffers, rendering to two eye buffers, which can be a non-trivial thing for code which is purely non-VR up until this point. So any texture format is fine for now, but at this stage, check to see what sort of size eye buffers you're going to use, and there's a function call for doing that in the SDK. And you have a choice here, so you can choose whether to have the highest resolution of perhaps a 1:1 pixel ratio in the center, which then becomes more towards the edge as the distortion kicks in. You have a choice, basically. So this next step uses that function, and just rendering those two eye buffers side by side and having that running is this step. Then it gets a bit more exciting. So you've got, next step is to hook in the sensors. So you're going to be reading off the pose of the Rift, finding out its position, its orientation, and then feeding those into the cameras that you have for your two eye buffers. An important note here is you're going to be reading in extra data that's coming through from the profile. That's that profile that you set up with the configuration utility. So there are things like IPD will come through automatically from whichever the current profile is in the config utility. So this is going on at the moment behind the scenes. It may not always be that way, but that's being pulled in. So you'll calculate the eye poses from the SDK, and that's an important step to do just once. So you'll do it at the same time. You'll get both eye poses in a single function call, and then those will be used to render your two eye buffers. And there'll be matrices involved, so just getting that right at this stage is good. Using the correct projection matrix is also an important part of using the SDK, because with VR, you no longer have a sense of a symmetrical field of view. It's now an asymmetric one, because you see less towards your nose than you do outside. So that's something to be incorporated into your engine. I'll say a little more about that in a minute. Finally then, you'd want to be outputting to the actual headset itself. So the next natural step is to create a set of textures that works with the SDK and the compositor in the SDK. And this is actually a set of textures for each eye. So the reason you're working with the compositor within the SDK is that these are going to be passed in. And they need to be a particular format as well. So don't be tripped up by perhaps using the wrong format of eye buffer texture to create. It's going to be required in sRGB format into the compositor. Anything else or incorrectly labeled, and it's going to be over bright or under bright or any other mismatches which you don't want. So just being mindful that there is a specific format required there. Then you're going to pass in a simple OVR layer. Now, layers is something which is quite a large topic, and we're covering it in a later slide. But for now, we're just going to use the simplest variety, which is an eye field of view one. And then instead of presenting to the screen, we're going to submit these eye buffers into the SDK. And now the image is in the HMD, not on the monitor. And another tip that we advocate to developers is try to avoid rendering, in fact, do avoid rendering to intermediate textures and then copying those into the eye buffers required by the SDK. It's best to just do that all in one go, straight to the render textures used by the SDK. So last step, we just show you in this sample how to create a mirror texture and copy resource to that texture. And a very important note is to not vsync to that mirror window that you're representing the scene outside the HMD on. Because if you synchronize to that, you'll then be at the wrong refresh rate, and it's very important to be using the HMD's refresh rate. So this is perhaps something that comes up every now and again with developers where they inadvertently vsync to that mirror window. So it's something to be avoided. Okay, so that's kind of a couple of methods of integrating VR in a basic way. The next important step is, as many of you have probably realized, the thing about VR is that getting it nearly right is unfortunately not quite right and not good enough. And the results of perhaps having small errors creeping in is that you might inadvertently have hidden discomfort. And unfortunately, the nature of this hidden discomfort is that it's hard to tell it's there. So really, part of our troubleshooting efforts and helping developers is to help identify these subtle errors, and we're going to be flagging the kind of top 6 with you now, just to kind of forewarn you about the kind of things to look for, which should help a lot. There is a little bit of general advice that we can give. I tend to encourage developers when I see them, if you're putting in a new VR option or feature, to try and exaggerate it if you can, just to really kick the tires on it and see whether it's doing exactly what you think it's doing. So a couple of examples with world scaling, where this is a situation where you have some art assets and they're perhaps not 1 unit to 1 meter like the SDK provides its poses. So you're going to want to, instead of redoing all your artwork, just readjust the VR parameters. So doing this wrong, it can show up quite badly in terms of kind of hidden discomfort. We have another Oculus from Tiny sample called World Scaling, which shows an exaggerated version of really minimizing something or maximizing the scale. And in doing that, you can see, you can get a sense of whether your code is actually doing the right thing, so that when you then have the more subtle scaling, which you probably will have, you can be more reassured that that's correct. Another example of how to exaggerate an option is perhaps in your code base you supply eye buffers to the SDK at perhaps not 1 every frame, perhaps it's every other frame or less often. And so to show that the SDK in your code is running correctly, then perhaps take an extreme and just freeze providing any more eye buffers. So effectively freeze time warp. It's like a sample that we provide, and it's like the picture there. You basically don't supply any more eye buffers, and you check that the SDK in your code is doing the right thing. As you turn around, the image stays looking kind of right, but disappears off because it's not being updated by what's in front of you. So another very good indicator that perhaps something might be amiss is if you're in VR and you're spending, say, 5 or 10 minutes inside a virtual world, if you take the headset off and then you have a sense of kind of readjusting to the to the real world again, kind of your eyes are perhaps sort of just that moment of readjustment, that's a very good indicator that there's something not quite right. So do take note of that if you find that happening. It's particularly when you're coming out of VR, this comes up. Another tip that I'm asked quite a lot is, now that developers are getting good latency, very low latency values, below 20 milliseconds, a way to just immediately see, get a good sense of what your latency is to, there are ways of doing this, but a quick rule of thumb way is to just be in VR and then just look at a vertical edge or a vertical edge of a wall and just shake the headset to the side quite strongly. And depending on how much that wall moves, that's how much it gives you an indication of the latency involved in your code. So if shaking it like this and it's just hardly moving at all, that's great. And then proportionally to how much it moves, that's how much latency you can kind of see in an instant. So moving on then, so the top 6 things we found at developers. The number 1 is performance. Absolutely vital within any VR application is to very solidly hit the frame rate of the HMD so that you don't have any missed frames, because anything like missed frames or being consistently out of the correct frame rate will manifest itself as judder, and that will mask other issues that you have in VR. It will break presence, it will look bad, perhaps create discomfort. So judder is absolutely to be avoided, and this is something that Scott will be talking about shortly, about how to profile and get this ensure you have this performance. for now, I'll say that because this is an issue that you absolutely want to remedy, within the SDK we provide a mechanism, some headline performance values and graphs so that you can just enable and then see immediately how your code's running. And there's a sample performance head-up display, which is one of the Oculus from Tiny samples, which shows how to turn this on and use the different pages with the different headline metrics and graphs. So another thing, because we're aware that developers, you obviously will be optimizing your code to get to the frame rate, but perhaps initially you want to try something and it isn't, it needs optimizing, it isn't immediately at the top frame rate. An interesting option to do is to be able to reduce the content on a switch so that you can, at any moment, guarantee that you can at least revert back to the correct frame rate. And then you can check the rest of your code, because the thing about Judder is that it's so intrusive to getting good presence that it can hide other VR issues. So if you have such a switch as this, that's a useful thing to have. We find as well, quite a subtle thing, the head model, the way that the developer will use their code to give the correct response to the Rift pose. That's something that we find flaws in it from time to time, and in fact fairly often. So this is where you really want to be having in your VR world, you want the correct response to turning your head and positioning your head as if you were in the real world. The common causes of getting this wrong are world scaling, which I've mentioned before, where somebody's attempted to change the scale and just something's not quite right. There's a little tendency to introduce an extra neck bone. We've found that from a few developers, where instead of understanding the pose from the SDK as being actually where the screen is and in the right position, they've perhaps understood it to be in the middle of the head, and so have provided an offset to where they feel the HMD is, and this isn't needed. And in fact, if you do provide that additional offset or neck bone, you then get unwanted positional translations every time you rotate, and that is a potential cause of discomfort. Another item is matrix ordering when you do your maths to convert these orientations or positions. Because of the subtlety of some of the movement, it can be hidden, particularly positional movement. You can accidentally put the wrong thing in, and so a way of resolving this and diagnosing it is to exaggerate what's happening and just see, are your maths, your matrix combinations, are they all working correctly for an exaggerated situation? And then you can put it back to how it should be. So because this is quite a prevalent issue, we've taken steps to build in, again, into the SDK, some diagnostic tools that you can use. And in this particular case, we've provided a correct quad, which is that orange kind of blotchy thing up there. And we've provided a quad that you can summon up within the SDK, and that is a correct VR for that quad. And the sample debug HUD will show you how to summon that up and how to position it and scale it, translate it, put it where you like. And then the way to use that is to align that sort of fairly closely with some of your artwork, and then move your head around, reorientate, reposition, and check that you have no relative movement between your artwork and this correct quad. And if you do have relative movement, then that needs to be investigated and fixed. And actually that really is sort of 95% of correcting for incorrect head model is just to diagnose that there's an issue there at all. So that's really helpful to use, and I'd encourage you to turn that on in your code. Another issue that we've found surprisingly often is errors in using the correct IPD, the interpupillary distance, and inadvertently perhaps setting that to 0 and having no 3D-ness whatsoever, so no stereoscopic 3D. This happens surprisingly often, and it's made possible, I believe, by the fact that there is some great artwork out there. And when you have great artwork, your brain has a lot of cues of where things are depth-wise, and so you find that this is enough to convince your brain, oh yes, this must be stereo, when in fact sometimes it isn't. So we've provided one sample, which is a just IPD, which is it's kind of showcasing what happens if you were to switch IPD to 0 and then back up to a normal value and perhaps some extremes. And it's really most visible when you have an IPD problem. If you give it extremes or if you turn it off and on, you can quite obviously see the difference when you have a stereoscopic scene and when you don't, by comparison. Because this happens fairly often, and in fact, when I'm at developers, if there's any suspicion that the IPD or 3Dness is not correct, then I encourage developers to put a crosshairs or a dot or something at the center point of the two eyes. And rather than getting every developer to do this, it's built into the SDK that we now, you can just switch on this crosshairs, and it'll be at the center. And then the way to use this is to see the various parts of your scene, sort of line it up with that crosshairs. So if you look at the example, I've zoomed in on, I've put the crosshairs there, and I've zoomed in on the sections of the left and right eye. And you can see that in the distance, the railings, because they're a distant object, there isn't much sideways distance between the left eye and the right eye. And yet for a near object, such as the near posts, then you can see there's quite a significant difference between left eye and right eye. And that's what you're looking for, just to check loosely that you seem to have correct IPD in there, and look for that to be adjusting as you go off in distance. So part of this is potentially caused by, our SDK has varied over iterations, and I believe originally we used to oblige the developer to put in these offsets for IPD, and then in later versions, the SDK did it for you. So that's why occasionally we get like a double batch of IPDs or none at all. So just be aware of that. Another check to make sure, a very good check actually, to check that your IPD and stereoscopy is right, is to look at look at the positional tracker. Like put a representation of that inside your code, so a 3D object that is the position tracker. And then when you're in VR, if you reach for where you think that object is, if it's exactly where you think it is, then great, everything's going really well. If it's slightly behind or slightly in front, then you know you have a mismatch in something IPD related. And of course, if you have really no sense of where it is, then you might perhaps have a monoscopic scene. We have found developers where they have seemingly a very good frame rate, it's all very smooth and judder-free, and yet there's this kind of micro judder going on where, particularly with thin objects like lampposts, if you move side to side, you kind of see multiple images, just little bit subtle multiple images as you turn your head. And the cause of this is when developers call the eye pose, so you call for the eye poses, then you render your two eye buffers, then it can be tempting for some developers to get a fresher version of the eye buffers and then submit those to the compositor in the SDK. The thing to do is not to get a fresh one. So the call for calculate eye pose that got you the pose that you then rendered your eye buffers with, that's the one you need to pass in and submit into the SDK. Something that can be misunderstood, particularly developers going from non-VR to VR, is how field of view works and eye resolution. So field of view particularly, in traditional non-VR applications, it was something where we had the choice, we could have wide angle or we could zoom in, whereas in VR it's very much an attribute associated with clipping. So if you change the field of view, that's how much of the screen you're actually seeing. The best description of this is actually if you look at the vary field of view sample, which allows you to vary that field of view, and you see exactly what varying field of view does. So that's very illuminating. The other thing to be mindful, particularly if you're introducing VR into your engine, is to remember that now field of view is an asymmetric quality. So whereas we used to have it very symmetric, now if you stick with a symmetric field of view, then you find yourself being very wasteful in terms of rendering too much out of the sides. So best case, that's kind of wasteful. Worst case is it can actually, if you then hook those in incorrectly, you can create bad distortion, which is very uncomfortable. So another item that is a tiny bit misunderstood sometimes is the eye buffer resolution. Now it definitely isn't the half the HMD resolution. It's something where you get to choose, and on a per application basis, you might choose to have very high resolution buffers, eye buffers, or you could perhaps have lower ones. And in fact, it's worth exploring whether you can have a lower resolution so that you can gain back some performance. So these are both things that can be varied, and they're both potentially can get back performance. Finally, we've met with the odd developer who's perhaps had a previous adventure in sort of stereoscopic viewing, perhaps with red and green glasses or some other kind of older technology, and where they've been tempted to reuse the code, perhaps because it has similarities between having two eye buffers. Be very wary of doing this in case you accidentally put in some wrong assumptions. For example, in VR technology and using the Oculus SDK, it's parallel eye views between each of the eyes, not converging ones, as perhaps might have been in the past. And avoid the temptation to try and reuse code and then just put a correction factor in there, because to make it look kind of right, because those are quite difficult to debug, and they are in fact wrong and could create discomfort. And so chase down anything. So be mindful of reusing legacy code. Anything that looks wrong, try and chase it down. And sometimes if you find you have compounded a couple of errors or more, then just peel back that code to something which is kind of pure VR, sort of akin to the sort of integration examples we gave. And then if you still think your effect is good, then layer it on gradually and check that it's the right thing to do. Okay, so that's kind of the basic integration and troubleshooting. On from that, you'll then be tempted to explore more of the features of the SDK, and so there are a whole raft of Oculus Room Tiny samples, as I mentioned, and these are all in one solution. They're downloaded with the SDK, and so we have the basic Oculus Room Tiny, and then we have the more advanced sort of how to use the features, the common features, and we even go into kind of an experimental territory where we've tried something out, and we're not necessarily advocating it, but since we've tried it, we're happy for you to have a look at it and see what you think, and perhaps, in many cases it might be that you can innovate further than we have, or there's some facet that you think that could be very useful. So we've provided, again, simplistic source code for these sort of adventures that we've tried as well, in the hope that they save you some time and perhaps give some ideas into innovating further yourself. So I'm going to mention just a few of these. So one of the features that you'll pretty quickly want to get to grips with, I imagine, is knowing where your user is within that position tracking cone. So it's important to make sure that your applications can keep the user within that cone, to know where it is. If it moves, then you need to kind of keep track of that. So there's a simple sample we call just camera volume, and it just shows some of the nuances of making sure that you offset the position that we give you for the tracker in the right place in the coordinate system, and also be aware that its orientation is actually a live changing value. So it's tempting, it has been tempting in the past, I think, for the odd developer to kind of assume that it's a horizontal thing, because we usually put it horizontally, perhaps on top of our monitor or something. Whereas in fact, even if it seems horizontal, there is an angle, we're feeding it in, and in fact if that angle changes, then that will be fed through by the SDK, so you need to kind of follow any angle changes that might be happening live. There's also one or two optical illusions which are quite interesting, where given the fact that if you represent this tracking volume in your code, if you choose the UVs perhaps somewhat, just arbitrarily, you can get some splendid optical illusions where it appears to be, your brain tries to interpret this cone shape as kind of a cube. It's quite interesting. There are examples, there are notes inside the sample about that. One note I would make that I find is useful for developers is if you find you're outside of that tracking cone and the SDK signals to you no longer tracking, then don't be tempted to kind of ignore that SDK position pose, because it's still feeding you something useful. And in fact, once it loses the positional tracking from the camera, it then continues with a head model where it puts in a positional offset according to your head orientation. So even if you lost tracking, just continue to use that SDK position pose. And we provided a couple of examples of what you might want to do if you get close to the tracking volume or go outside it. By no means exhaustive, just a couple of code examples for you. We're probably all very used to the kind of iconic representation of a VR application on the monitor with its two distorted eye buffers. But it doesn't have to be that way at all. And in fact, we present a mirror variance sample where we show you how you can have, instead of the two eyes, you can have one eye. You can choose to show them distorted or undistorted or full screen. And in fact, it's much more user-friendly to have just a single eye and perhaps undistorted. And we'd kind of recommend that. But this sample in particular is a way of sort of showing you how to work with the SDK to basically put what you like on the mirror window and perhaps even a sort of window into switching between sort of VR and non-VR. Something else to be mindful of is because some of these aspects expect the certain texture format. So be mindful, you can actually have different brightnesses in your mirror window as you have in the HMD. So just always be mindful of what texture format is being used with the mirror window and with the eye buffers. Layers is one of my favourite parts of the SDK, in that it provides a lot of flexibility and creativity for developers to use. What we do is we provide these layers of VR whereby you can choose different areas of the screen where you might have perhaps more resolution, or parts of the screen might go at different frame rates. Very flexible, and you can combine these layers. In the example there, I'm showing the central region of the screen is at actually full frame rate and high resolution. And then the purple tinted bit is a lower resolution, much lower, and actually much lower frame rate as well. It's not being updated as often, hence it's sort of disappearing around, because it's still being time warped. So a lot of possibilities there to use this layers functionality. And there's a lot of comments in the code and documentation too. Also, for getting more readable text, again, layers is very useful for that. You could either have increased resolution, perhaps where your text is, where that area of the screen is, or you can even, this layers functionality supports you being able to render a quad directly onto the screen of the HMD. So you bypass the eye buffers altogether, so you have the best quality text or graphics coming all the way through. Another thing that we provide some samples on is alternate eye rendering. It's kind of a tempting way of gaining back performance. So instead of rendering the 2 eye buffers every frame, you can perhaps just render 1 eye buffer each frame and then use the older image from the last frame and time warp that into position. So we have samples for this. There are artifacts though, so it's something to be very careful of using, particularly with any animating objects. You find that you see double images and that kind of thing. And also, a strong warning about doing a simplistic version of this is if you just simply render one eye, use the old one, render this eye, use the old one, you can actually create 2 images that don't stereoscopically match. And this can create discomfort as your brain tries to fuse between 2 images that essentially don't fuse, particularly for close objects. This is particularly bad if you're strafing sideways, where your effective IPD kind of shrinks and then grows. So if interested in alternate eye methods, then the stereo matching version is the one to use. So we provide a sample for that. There's a bit more logic, and you kind of hang on to the older eye buffers until you have a stereoscopic matching pair. That's much more comfortable. You've still got the artifact of the moving objects, but for some applications, maybe that fits. Very interesting technique as well, I'll just mention, which we provide some samples for, is monoscopic rendering, where I guess that's where you only render 1 eye buffer and then you share it between the two left and right eyes. Now, we're not advocating that you do a monoscopic application, because it's such a shame to not have that glorious 3D. We do provide a sample which shows monoscopic use of the SDK. However, what's much more interesting is if you take advantage of the fact that pieces of the geometry beyond a certain point are not quite so obvious. It's not quite so obvious once they cease to become stereoscopic. So in a discrete case, you might have a cockpit game where you render everything in the cockpit in stereo, so you render both eyes. Then everything outside the cockpit you perhaps render once and then share between the 2 eyes. So we have a sample for this. We also have a sample where you have the more continuous case, where you have the scene you can see up there, where you draw the foreground, you draw the left and the right eye images as normal, and then beyond a certain point into that kind of purpley area, you then just render it the once, and then you offset it into each of the eyes, such that it's kind of stereoscopically planted at the point where you cease to do stereo rendering. And this creates a no seam whatsoever. And surprisingly, you can get very close, you can do this overlap, this seam very close. And so you get all the savings of only having to render everything beyond that seam just the once. So interesting technique. So as I mentioned before, that one of the big things is getting your performance to be within solidly at the frame rate of your HMD. So I'm now going to hand over to Scott, who's going to talk about profiling your VR app.
Hi, I'm just going to put this over here. Hi, good afternoon, everyone. So my name's Scott, and I'm a senior software engineer in the developer relations group. I'm going to spend the next 10 to 15 minutes discussing how we profile VR apps internally at Oculus. As Tom said, it's absolutely critical that, It's absolutely critical that your rendering finishes before each V-blank, so profiling is very important. So let's get started. So the first thing I want to talk about is GPU tools. I know a lot of you guys use them to capture frames and make sure that your rendering's right. At this time, all of them work. NVIDIA Insight 5.0 RC1 has an issue with the mirror window where the mirror window doesn't show up properly. But other than that, you can capture a frame and you can view all that stuff. All the other stuff in those tools, though, with like profiling and stuff, it might not be applicable to what we do. So let's go over how a typical Oculus app works. So on the left side here, you can see you have your app, and you create your eye buffers, and then you send them over to our OVR server process through a submit frame call. Our OVR server process performs the chromatic aberration correction, the distortion, and the layer compositing. And then it finally sends the image to the HMD. Additionally, if you ask for a mirror texture back, it'll return that to you. As you can see here, this is like a multi-process approach, so because of that, it's hard to use those other tools that currently exist that people typically use. So internally, we use GPU View. I'm not sure how many of you are familiar with GPU View. GPU View is a tool that was developed at Microsoft to see GPU work being done across the whole system. It does this by building graphs based off of GPU-related ETW points. ETW points are basically event points that you can just inject through all your code, and it logs them to a file. Then later on, you can view them. And Microsoft has put a whole bunch of points throughout their graphic stack to make it easier to see these types of things. Additionally, GPU View works on packets instead of normal draw calls. So what typically happens is the drivers will start building up a whole bunch of work into one packet, and then they'll send the packet across. And we'll go over how all this works in a little bit. Therefore, you can see that this tool allows us to view both processes work and make sure that both finish before the V-blank. So let's get started on the tool. So the top section of the tool is this blue area, and that represents the hardware queues that the actual GPU is working on. If you look on the left and right, there's these red vertical lines that I've highlighted with these yellow squares. Those represent the Rift's V-blank in this situation here. So in this case, you can see that we finished quite a bit early before the next V-blank, so that's good. This is taken from Oculus World Demo, which is a relatively simple app. Next is these purple bars here that I've highlighted in yellow. This represents the app's work that the app was doing. The bottommost bar represents the packet that the GPU is currently working on, and going from left to right is time. Now you can see directly after that is these green bars, and that's our compositor process doing all of its distortion and time warp and everything that I mentioned earlier. Okay. I've highlighted this section here of our process doing its work, and in the bottom right-hand corner over here, it gives you how much time it took to do all that work, and it took around 1.3 milliseconds in this case. It varies depending on the GPU's work. This was done on a GeForce GTX 980, and I've seen it normally take around 1 millisecond, though. Next, below that is all the different processes that are running on the system. You can close all of them and only show the ones that are relevant to you. So here I've shown our compositor process. It's basically broken into two sections, and we'll go over both of those sections. So the top part is the device context area. This represents the GPU packets that have shown have been submitted to the server or to the hardware, but haven't actually possibly been scheduled yet, and they will eventually get scheduled. Their starting times are earlier than what you'll see on the hardware because it takes a while for the OS to actually transfer it over there. Their ending times will be very close because once the hardware is done with it, the driver will notify the OS, and the OS will schedule event that says this happened. Below that is the CPU threads that GPU view thinks are relevant. Not all of the threads are shown, but you can easily go up to the menu and display all of them. Right here, it thinks that there's like 3 that are relevant in this case. Okay. Next, we're looking at Oculus World demo, the app. I've highlighted a yellow block here. It's kind of hard to see on these slides, but it has like a cross-stitch pattern, and that represents a present call, like a DXGI swap chain present. This is important because it actually happens after the VBlank because we have our own VBlank, which is separate from the desktop's VBlank. And below that is the user mode driver. In this case, this is NVIDIA, so it starts with NV WGF2M. Typically, apps will make Direct3D calls that will eventually get handled by the user mode driver. At certain points, the user mode driver will determine that a GPU work packet is ready and inform the Direct3D runtime that it should be passed on to the scheduler. The user mode driver also handles shader compiles, texture swiveling, and other stuff like that. So you might see other threads pop up and doing work. If you see a lot of work going on one of these threads down here, it might lead to a stall, so you should look into that more. The Oculus runtime in 0.7 comes with a bunch of ETW points that you can install and view in GPU view. All of them begin with OVR, so we'll go over a couple here. So the first one is these red vertical lines, which represent our hardware VBlank. GPU view has a view visible vsync under one of the menu items, but that doesn't match our hardware, so we had to create our own. One issue with this, though, is with IHV direct mode, NVIDIA and AMD have their own, and we're still working with them to get those exposed. But if you use our direct mode, then you can easily see all of these. The next one I'd like to talk about is our distortion ETW points. So if you look up here, there's 2 vertical red lines. They're representing the start and stop of the CPU work to generate all of the GPU work. Immediately after that, you see these green bars starting up, and that's the GPU work that we were doing earlier. So now that I've talked about that, I'd like to go over like our queue ahead and show before and after and show how it works in GPU view so you can easily view all this stuff. So right here is a frame of a queue ahead sample that we have in the SDK. And if you look up in the top left, you can see a red square around some bars that finish after the red vertical line. So this represents that we missed the VBlank for that frame. Additionally, it happens again at the end of the next frame, too. So after that happens, we come back to the app, and the app wants to update its mirror windows. So you can see that present happening right there with the red stitches on the bars. And then after that, the app starts working on doing all the CPU work for the next frame right here in the bottom area with the green bar, which eventually leads to NVIDIA's driver starting up here to create some packets of work. And then after that, it schedules the first packet right there with the red square around that green bar, which eventually gets scheduled onto the GPU here. So luckily, it didn't take that long from when NVIDIA submitted the packet to it actually getting ran on the GPU. But if you look from the beginning of the left red line to that, it's like almost half the frame is gone already. So it's like way late to start doing your work. So that's why, in this case, we're missing each VBlank. So in 0601, we implemented queue ahead. And what queue ahead does is it returns to the app a little bit earlier, allowing the app to start doing all the work a little bit earlier too. So if you look here, I've highlighted where the present now happens, which is a quarter of a frame earlier than before. And then after that, the CPU starts doing all of its work, which is overlapping in the VBlank in this case, but it's quite a bit earlier than before. And this, oh, sorry, go back one, sorry. Oh, I'm missing a slide. And this leads to the GPU work actually starting quite a bit earlier. And now if you look on this side, we're like a lot earlier from the VBlank, so we're finishing in time. So now it's hitting frame rate every frame. So how do you use like GPU View? Well, the first thing is you have to go download it from the Windows SDK. And then from the administrator command prompt, you just run our install.command once. It'll install all of our ETW manifests. And then to make a GPU view capture, you just run ovr log.command. It comes with our runtime in the same directory as the other stuff. This will start the logging process, and then you just run your app, and then whenever you're done, you just run ovr log.command again to stop it. These files grow really big, very, very fast, like multiple gigabytes, so you should limit how much you're going to capture. But you can capture at any point, so you can have your app running and then go to a certain point and then start capturing. Once that's done, it'll create this merge.etl file in the trace folder, and you can just open GPU view, and it takes a little while to load, but then eventually everything will show up. Additionally, if you'd like more information on GPU view, I recommend these two links right here. You can just easily search for them in Google. The first one, Matt's Web Corner. Matt was an intern at Microsoft who wrote the app originally. It's been moved on to a bigger team now. And the second one is John Story in GDC 2012 gave a talk on using GPU view to understand DirectX 11 games. And it's really good because he goes more over driver-related issues that you could see. So I'd like to bring Tom up to conclude our talk.
Great. Thanks, Scott. Yeah. So, thanks. So, in conclusion, then, there is this wealth of tools and downloads and the SDK and its samples that is there for you to use. So, in conclusion, we've outlined these two methods that you can use to integrate VR into your non-VR code base. And we've kind of given an insight into all these samples that are available to show not only the basic use of our SDK and to get good VR, but also extended SDK usage and how to see within very minimal bits of code how you might do the various features within VR, plus some experimental things too for you to look at. I hope it's been helpful that we've flagged some of the common items that have come up with developers. Forewarned is forearmed, as I said earlier. So I hope that's been useful. And then, of course, Scott's given an insight into kind of the profiling that really is a very good thing to do with VR in order to ensure you have that solid frame rate, which is going to deliver the presence that you really kind of want within a VR product. There is some even more information available. So within our developer portal, which is off our main website, you've got documents, there are blog posts about some of the interesting aspects of VR development. You've got the downloads of the runtimes and the SDKs. And also within that, you've got forums, which developers and ourselves are very active. And so you can see shared experiences and where people have had issues, or we've offered solutions and answered questions. Same with Answer Hub. That's another place where you can ask things and see what other people have asked, and generally just absorb that knowledge and shared experience from other developers. And finally, is the developer relations group of which Scott and I are part. And we, our goal is to very much get you to be making the best VR that you can and equip you to do so. And we're available, via email or on the telephone, or as time allows, in person as well. So, as been said before in other talks at Connect, we really are really excited to see the kind of VR experiences that you come up with and how you innovate with our SDK. So that's something that everyone at Oculus is really excited to see, what comes next. So thanks very much for your attention. And at this time, we're very happy to answer a few questions. There's a microphone there if you want to step up to it, but very happy to take questions. We must have covered everything.
Yeah, I guess so.
Well, if there aren't any questions, there.
I have one. Sorry, I have one question. It's a little off topic. I just want to know what the process look like inside Oculus when you testing all this stuff. Because right now it's really hard to write some code on computers and check it in headsets. Do you have some kind of special headsets maybe for testing all this stuff, or you're using the same headsets we are using as developers? something like where you can just put it, not to remove it from your head all the time and just slide it up and write code, test, slide it up.
Yeah, I guess development-wise, putting things, a combination of testing in the Rift, testing on the mirror windows, sort of outputting data to mirrors on the screens themselves. If we also do an awful lot of testing internally at Oculus for making sure that subsequent SDKs are all working well. So we have a certain amount of automation involved. So it's getting more and more thorough and exhaustive, the tests that we do. Does that answer the question, or is there some extra?
Okay.
Great. Any more questions at all? Well, as I say, there is that information on the website, and dig into that, and there's the download. So I guess to visit our developer forum, and good luck. Thank you.